Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today's lecture is about the normal and ectopic pacemaker and reentrant phenomena. At the end of this lecture, you will be able to learn how and why SA node acts as pacemaker of the heart. What is the concept of ectopic pacemaker and which components of the conduction system can act as pacemaker? What happens when ectopic pacing occurs in the heart? How does it leads to overdrive suppression and Stokes-Adams syndrome? What is the mechanism of re-entry and its relation with unidirectional block? Basically, this is the necessary condition for the occurrence of re-entry phenomena. We will start our discussion with SA node, that how SA node acts as pacemaker of the heart. The answer derives from the fact that the discharge rate of SA node is greater than other areas of the heart and conduction system, like the discharge rate of AV node is 40 to 60 times per minute, while the discharge rate of Purkinje fibers is 15 to 40 times per minute, and these rates are less than the rate of SA nodal firing, that is between 70 to 80 beats per minute or times per minute. Each time when sinus node discharges, the impulses passes through interatrial pathways to AV node. Then excitation of the AV node occurs. Then from AV node, impulses passes through bundle of his through branches of his bundle, right and left bundle branch, to the Purkinje fibers. And then from the Purkinje fibers to the ventricles. When impulse passes through different parts and completes the process of excitation of the heart muscle, then next again SA node discharges and This again excites all components and ventricles before either AV node or Purkinje fibers can reach their threshold of excitation. This is how we can say that the SA node controls the beat of the heart. Occasionally, some other parts of the heart develops a more rapid discharge rate than that of SA node. And this occurs under rare conditions when a place in the atrial when a place in the atrial or ventricular muscle develops excessive excitability, then SA node, then that part in the atrial or the ventricular muscle can act as pacemaker of the heart. Usually, this ectopic pacemaker of the heart, it occurs at the AV node or AV bundle or the Purkinje fibers. Mostly, it occurs either at the AV node or in the Purkinje fibers. And this occurs due to block in transmission from SA node or SA node to AV node, or as we mentioned already, develops due to excessive excitability of AV node or Purkinje fibers. This concept that some other part of the heart can act as a pacemaker is called ectopic pacemaking. And any part, the normal, as we mentioned that the normal pacemaker of the heart is SA node. So any other part than the SA node, if it acts as a pacemaker of the heart, then it is labeled as ectopic pacemaker. When ectopic pacemaking occurs, when this occurs, what happens? two conditions occurs. Number one, the atria continue to beat at normal rate. Normal rate of rhythm of SA node. As SA node generates impulses, SA node generates impulses that depolarizes atria. Secondly, the ectopic pacemaking causes an abnormal sequence of contraction of different parts of heart, and this leads to and produces significant debility of heart pumping. When ectopic pacing occurs due to defect at AV node, it leads to AV bundle block. After sudden AV bundle block, Purkinje system does not begin to emit impulses until 5 to 20 seconds later, and this occurs because Purkinje fibers had been overdriven by fast impulses from SA node. This consequently produces suppression and the Purkinje fibers are therefore in a suppressed state. When impulses fail to pass from Purkinje fibers to the ventricular muscle, then the ventricles fails to pump blood during these 5 to 20 seconds. Due to this, the person faints after the first 4 to 5 seconds because of blockade of blood supply to brain. This delayed pickup of heartbeat after 5 to 20 seconds is called Stokes-Adam syndrome. If this delay period is long, then it may lead to death of the patient. Now, under rare conditions, a cardiac impulse may re-excite some region through which it had passed previously. And this phenomena of re-excitation is known as re-entry phenomena. This re-entry phenomena underlies many clinical disturbances of rhythm. This re-entry may be ordered or it may be random. When ordered re-entry phenomena occurs, the impulse traverses a fixed anatomical path. When random re-entry phenomena occurs, the path continues to change, and the principal example of random re-entry is fibrillation, and this is life-threatening condition. I will explain the phenomena of re-entry with the help of four diagrams: A, B, C, and D. In each of these four diagrams, a single bundle S divides into left and right branch with a connecting branch between the right and left branches. C is for connecting branch. Normally, the figure A of this slide shows normal passage of impulse transmission. Normally, the impulse coming down the bundle S is conducted along left branch and the right branch. As the impulse reaches as the impulse reaches and enters connects link C from both sides from both sides and becomes extinguished at the point of collision. This is the point of collision. The impulse from the left side, the impulse from the this left side it cannot proceed further and stops here because the tissue beyond has just been depolarized from the this right direction, and therefore it is absolutely refractory. As we defined absolute refractory period, the period during which a second stimulus, no matter is the strength of the stimulus, cannot re-excite the already excited muscle or nerve fibers. Therefore, the impulse cannot pass through bundle C either from the right neither from the left for the same reason of absolute refractory period. If we see the panel B of this slide, it shows that the impulse from bundle S passes through the left and right branches, but it cannot proceed in the anti-grade or forward direction because of block as shown in the blue box. If we see the panel C of this slide, the impulse along the S bundle, it passes through the left bundle and it passes through the right. But on the right side, this is the block in the blue box. Therefore, the impulse through this right box cannot pass in forward direction. So the impulse is blocked in the branch R. Now what happens along the branch on the left side? The impulse passes along the left branch, then it proceeds through the this C, that is the connecting branch, and it passes retrogradely. It passes in the retrograde direction, but it cannot but it cannot it cannot cross the block in retrograde direction. Therefore, such kind of block is labeled as bidirectional block. The figure D of this slide, it shows unidirectional block that exists in branch R. Now the impulse along the branch S, it passes along the branch on the left side, then it passes through the connecting branch and proceeds in the retrograde direction, and it crosses this blue block in way of branch R and passes in the retrograde direction to form a re-entry loop. From this point, again impulses passes through the left branch, then from the left branch, again in the retrograde direction through the connecting branch, then it again crosses the block in way of branch R, and then again re-excites the area from where it already passed, and then again enters the branch on the left side. So in this way it forms a re-entry loop. Therefore, on the basis of this, we can say that a necessary condition for re-entry loop to result is unidirectional block. As shown in the panel D, the impulse may travel down the branch L on normally, and it may be blocked in the antigrade direction in branch R. The impulse that was conducted down branch L and through the connecting branch C may be able to penetrate the depressed region in the branch R from the retrograde direction, even though the antigrade impulse was blocked previously at this site. The antigrade impulse arrives at the depressed region in branch R earlier than the impulse that traverses a long path through branch L and then through connecting branch and enters branch R from this opposite or retrograde direction. The antigrade impulse may be blocked simply because it arrives at the depressed this blue area is the depressed region. It arrives at the depressed region during its effective refractory period. If the retrograde impulse is delayed sufficiently, as we have seen in the branch on the left side or the branch L, and then passes through the branch C, that is a connecting branch. If this path is delayed sufficiently, the refractory period refractory period may have ended. Refractory period may have ended and the impulse is conducted back into the bundle S, and then from bundle S it again passes into the branch L and for a short distance into the branch S. So therefore we can say that the unidirectional block is a necessary condition for re-entry, but not a sufficient one. This is how we can explain the phenomena of re-entry loop that is the basis of many clinical abnormalities that leads to clinical arrhythmias, especially fibrillation, that are life-threatening complications. Thank you very much, dear students, for being with me. In the next lecture, we will start discussion on the electrocardiogram. Thank you very much.